Good afternoon, class. Chapter 4, Application of Derivatives. Here's section 4.6, Antiderivatives. 4.6, Antiderivatives. So again, as usual, a lot of formulas when it comes to differentiation. We should be comfortable with all of them for the sake of especially now the reverse process. Delta y and dy are explained here, and then linearization, simply put, finding the tangent line. Now, section 4.6, antiderivatives. When we say anti-differentiation or integration means the same thing. Integral calculus. Calculus has two parts. Differential calculus, which deals with instantaneous rates of change and slope of a tangent line. And integral calculus, which deals with accumulated change and area under a curve. Both parts rely heavily on the concept of a limit, and they are intimately related. Integral is the opposite of a derivative, also called antiderivative. Now the question is what? Given the derivative of a function, what is the original function? The reverse process of differentiation. So the antiderivative of f of x is the set of function capital F of x plus c such that d dx of f of x plus c is f lowercase f of x. The constant c is called the constant of integration. Class, when we differentiate, it creates one function and we are done. When we integrate, it creates a family of function because the derivative of any constant is 0. So we can have any constant. So that being the case, the antiderivative gives us that. And normally we use lowercase f to represent the derivative of uppercase f. Antidifferentiation is often called integration to indicate antiderivatives of x squared is x cubed over 3 plus c. We write the integral of x squared dx is x cubed over 3 plus c, or 1/3 of x cubed plus c. So the symbol here, the integral sign, was introduced by Leibniz and is called an integral sign. It is an elongated S and was chosen because an integral is a limit of sums. In general, the integral of f of x dx is capital F of x plus c. So capital F of x plus c is the general form of the antiderivative of f of x. Again, in short, when you differentiate, it creates one answer. When you want to go back, it creates a family of functions, which is called the general solution. So if we have two functions, capital F and capital G, and they are the antiderivative of f, in other words, capital F prime is lowercase f of x, and capital G prime is lowercase f, then capital F and G must be the same except have a difference of c. So you can say g of x is f of x, capital F of x plus c. So they differ by a constant, okay? They only differ by a constant. That's the concept. Let's do some warm-up examples here, okay? Determine these definite integrals, that is, find the antiderivative of each integral. When you want to differentiate this, first of all, this dx plays a huge role. It's a very important role, and it tells us what is the independent variable. Other than that, you have to be concerned with just 8. Think of something, you differentiate, and you get 8. Anything comes to mind? Any function? What can you differentiate to get 8?
8x.
Beautiful. So it's 8x plus c. And you check, if you differentiate this, it must give you this one without the dx, and it does. So check the dx of 8x plus c. Say. This one we've done already in the previous page. Think of something, you take a derivative, it gives you 3x squared, which is x cubed. So the answer is x cubed plus c. If you differentiate the right side, the derivative of x cubed plus c must give you this without the dx, so 3x squared. Now, how about here? Think about something, you take a derivative and it gives you e to the power of x.
E to the x.
That's it. So the answer is e to the power of x plus c, plus c. Don't forget the c. And to check, you differentiate the right side, and it obviously gives you this without the dx, namely e to the power of x. For this page, finally, the integral of 1 over x dx. Think about some function, you differentiate, the result is 1 over x. That's a natural log. So ln of absolute value of x, and you add a constant. The reason it's absolute value because the domain of a natural log is 0 to infinity. That's why we put absolute value. And so if you differentiate the right side, the derivative of ln of absolute value of x plus c, you get 1 over x. You get the integrand without the dx. So this was a warm-up example. Now, let's remind you of differentiation formulas. For example, the derivative of k times x is k when k is a number. Therefore, if we want to go that way, the integral of k dx must be kx plus c. The power rule, the derivative of x to the power of n is nx to the power of n minus 1. Therefore, if I differentiate the right side, nx to the power of n minus 1 dx gives me x to the power of n. Normally, we don't do it that way. Rather, we say the derivative of x to the power, the derivative of x to the power of n, and now we say the integral of x to the power of n dx. Now, which becomes 1 over n plus 1, x to the power of n plus 1, plus a constant, and n can't be negative 1. It's the reverse process. And I want to show you a little bit of a justification here. For the differentiation of x to the power of n, what do? First, we multiply by n, the exponent, and then we subtract 1 from the exponent, right? Now, for the integration, if I want to integrate the power, the integral of x to the power of n dx, the reverse process is going that way. Number 2 becomes number 1, and instead of subtraction becomes add 1 to n, which makes it n plus 1. And then instead of multiplication becomes divide by what we just got, which was n plus 1. So add 1 to n. So this one, add 1 to n and divide by n plus 1. Besides, just quickly, if I wanted to show this is true, if I differentiate this one, in other words, dx of the right side, okay, 1 over n plus 1, x to the power of n plus 1, and a constant, I get 1 over n plus 1 times n plus 1, then x to the power of n plus 1 minus 1, and plus constant gives me 0. And these two cancel each other. I simply put get x to the power of n. So this is the proof. I got the answer, okay? But I hope you pay attention to what I put for you here as well. Now, let's look at some examples we already know. The derivative of e to the power of x is e to the power of x. So the integral of the right side with dx must be e to the power of x plus a constant. Same thing here. If the derivative of ln of absolute value of x is 1 over x, the integral of the right side times dx must be ln of absolute value of x and a constant. This one, the derivative of sine is cosine, so the integral of cosine x dx must be sine. Now, the derivative of cosine is negative sine x dx, so of course, the integral of minus sine x dx is cosine x, but we don't want to say negative. So if you say what is the integral of sine x dx, this negative actually goes to the other side because you can multiply both sides by negative, right? If I multiply both sides by negative, this becomes the derivative of minus cosine x, and this becomes sine x. So here's the answer. The integral of e to the power of x dx is itself plus a constant. The integral of 1 over x dx. This one I want you to pay attention, and that is 1 over x is the same as x to the power minus 1. So ln of absolute value of x plus c. Now, the integral of cosine x is dx is sine x plus the constant, and the integral of sine x dx is minus cosine x plus a constant. The derivative of tan x is secant squared. So the integral of secant squared dx is tan x. This one, the integral of cosecant squared dx is minus cotangent x plus a constant. This one, the derivative of secant is secant x tan x. So the integral of secant x tan x dx is secant x and a constant. The derivative of cosecant x is minus cosecant x cotangent x. So the integral of the right side dx, the integral of cosecant x cotangent x dx is minus cosecant x and a constant. Constant multiple rule. If you recall, when we differentiated, if we had a multiplier, a coefficient, it would just remain there. So you can put it, leave it in the integral sign, or take it out, k times the integral of f of x dx. Sum and difference, the same thing. When we differentiated, we did it term by term. When we integrated, we do exactly the same thing here. The sum and difference work the same way. For example, the integral of f of x plus g of x times dx is the integral of f of x dx plus integral of g of x dx. For the derivative of e to the power of kx, we had the same answer times k. So the integral must be the reverse process. We divide by k. So the integral of e to the power of kx dx must be the same thing divided by k. So 1 over k e to the power of kx plus a constant. So very straightforward. So starting with this example, the power rule is used, the integral of x to the power of 7 dx. So we add 1 to the exponent, and we divide by it, and a constant. So when we add 1 to the exponent, becomes x to the power of 8, and this is 8. So 1 over 8, x to the power of 8, and a constant. Very straightforward. What about this one? We do the same thing. We add 1 to 99, becomes 100, and it becomes the denominator as well, and a constant. And the final answer is 1 over 100, x to the power of 100 plus c. If you want to go from here to the answer, that's just fine. The integral of square root of x dx. Same as differentiation, if you recall, we would change this so that the power rule could be used. So we're going to change this to x to the power of 1/2 first. Now we are going to use the power rule. That means we're going to add 1, and we're going to divide by it and a constant. So we add 1, 1/2 plus 1, and divide by it. 1/2 plus 1, everybody, is 3/2. 1 divided by 3/2 is 2/3. So the answer is 2/3 x to the power of 3/2 and a constant. The integral of 1 over x cubed dx, again, just like differentiation, we would change this so that the power rule could be used. So we're going to bring it up and make it to the power of negative. Now we follow the power rule. We're going to add 1 and then divide by it. So 1 over negative 3 plus 1, x to the power of negative 3 plus 1. Please don't forget the constant. So this is negative 2, this is negative 2, and so you can write this as negative 1/2. This goes down, so you get minus 1 over 2x squared and a constant. So these are power rules. Dealing with the exponentials, when we differentiate, we multiply by k. When we integrate, we divide by k. So the answer is itself, e to the power 4x, but divide by 4. The integral of e to the power minus 3x dx, the answer is itself. Divide by negative 3, that means minus 1/3 e to the power minus 3x plus a constant. E to the power of x over 2. If you see what you're dealing with, so be it. If not, let's rewrite x over 2 as 1/2 x. Therefore, we see that the answer is itself, and then divide by 1/2. So let me write that. 1 over 1/2, and then itself, okay? Don't forget the constant. 1 over 1/2 is 2. So in short, all the exponentials, the answer is itself. Whether you're differentiating or integrating makes no difference. In the case of a differentiation, you multiply by k. In the case of integration, you divide by k. So we divide by 4, we divide by negative 3, we divided by 1/2, which resulted in 2. Now, if you recognize this, so be it. If not, write 2 over x as 2 times 1 over x. You know the integral of 1 over x is a natural log. So the answer is 2 times ln of absolute value of x and a constant. So writing this way will help us see that we have a natural log as the answer. Same thing here. If you can see the answer, so be it. If not, just write it as 1/2 times 1 over x. This will help you see, again, it's the same answer here. Instead of 2, we have 1/2 in front. So 1 over x, the result is a natural log. So we have 1/2 times ln of absolute value of x and a constant. It will help us see, in all cases of natural logs, when you have 1 over x, the answer is natural log of x and a constant. Just pay attention to what you have in front. In this case, you have 2. In this case, you have 1/2.